Okay, so welcome and thank you for attending my first lecture on low-dimensional attractors and hippocampal representations. So I would like first to thank the organizers of this very nice summer school for inviting me to deliver these lectures. So today I'm going to talk about first principle approaches and theoretical analysis. And this lecture will be actually complemented tomorrow by another lecture on related issues, and I will introduce them later in a few slides. Okay, so what is going to be the plan today? So I'm going first to discuss briefly as an introduction the concept of attractors, going from discrete to continuous attractors. Then I'm going to introduce some very simple microscopic model for a single continuous attractor, how that works, and how it is connected to well-known models for the liquid-gas transition in statistical physics. Then I'm going to introduce ideas about multiple continuous attractors, how we can embed in a single neural networks many attractors. And I will discuss two ways of doing that. A first way, which was introduced by Samsonovich and McNaughton about 20 years ago, which is actually quite effective, but has some problems, and we will discuss the issues and the success of these models. And then I will introduce a more recent model, which is going to actually bypass the issues which are emerging with the additive learning rule of Samsonovich and McNaughton. And then I'm going to give you some summary and perspective and introduce what I'm going to do tomorrow. Okay, so what will be interesting throughout this lecture is the kind of network you see on the left, which is a network with n neurons, and these neurons have activity states, which may be continuous variable, which may be 0, 1. We will discuss this later in details, and they are connected together through some interaction coefficient Jij, connecting the neuron I to the neuron J. And so there will be some dynamical rules, which I'm going also to present, but essentially what is going to happen is that we, at any time t, will have an n-dimensional vector, where n is the number of neurons, of components fi, and that will define a single point in the activity space here on the right part of the slide. And this point will evolve over time as t is increasing. So the dynamical rule actually defines the evolution of this point, which may be extremely complicated. And in order to have well-defined dynamics, then we can think about this concept of attractors as a very important and effective concept. And the idea is that under some well-defined conditions, then maybe the dynamics of the network will converge towards a fixed point at long times, which is going to be exactly the attractor of the network dynamics. So starting from any initial condition, then the long time dynamics will converge toward this attractor. And this initial condition can be, for instance, some pattern of activity where some elements are disrupted by noise. And so this phenomenon of convergence is called pattern completion in computational neuroscience. So of course, there might be more than one attractors in this very high dimensional space. There might be multiple attractors, as you can see on the drawing now. And these attractors will be actually separated by some lines, which define basins of attraction. So depending on where the initial condition lie, so for instance, in the first basin here or in the second basin here, then the dynamics will end up in some of the attractors, in one of these attractors here. So there are well-defined and quite celebrated models to do that. And probably one of the most well-known model is the model that was introduced by John Hopfield in 1982 in his celebrated paper. I will come back to that in detail. So for a long time, these models have been quite theoretical models, but they have been also recently more helpful to understand the outcome of experiments. And I would like to briefly show one of these experiments, which was done by Batoli and collaborators. And what these people did is that they looked at the activity in the superficial auditory cortex of a mouse. And this mouse is actually subject to different sounds, sorry. And this noise, these sounds can be pure tones at a well-defined frequency. For instance, in the case I'm going to explain now, 26.8 kilohertz, for instance, single frequency, or another frequency, 9.5 kilohertz, or so on. So what you can do is actually, if you very gently remove a little bit of the external part of the skull of the animal without actually making any hole, so that the skull is still intact, so it's non-invasive. Then you can actually record the activity if the mouse has been genetically modified and the neurons become fluorescent when they become active. So here you see the kind of experiment which is done. So the activity is recording in a small patch here, which is about 200 micrometers wide. And depending on what sound is presented to the animal, you see that the activity is specific to this particular sound. So here you see for white noise, for pure tones at 4 kilohertz, 8 kilohertz, and 16 kilohertz. So you can record the activity of the neurons, which are identified here, and have a pattern of activity that is shown here. So first of all, the response is dependent on the stimulus. So here you see for a given frequency of 26.8 kilohertz, then 87 neurons were identified by the people doing the experiments, and see each column corresponds to a different repetition of the same experiment. So the response is noisy, but you can define an average response, which is specific to this particular frequency. And if you do exactly the same experiment and look at the rightmost panel here, at a different frequency, 9.5 kilohertz, you see a different response. They are clearly different. So this is specific to the sound which is presented. Now the question is, what happens when you present a mixture of two pure sounds with different intensities, which is a mixture between this 26.8 and 9.5 kilohertz frequencies? Then you can look at, as a function, as the intensity, relative intensity increases from 0 to 1 between the two frequencies at the typical response, and do some kind of correlation measure between what you get for intensity, for pure intensity at 26.8 kilohertz, and what you get when you have a mixture. And this is exactly what is shown here in this matrix on the rightmost panel here on the screen. You see a very strong correlation if this relative mixture fraction is below some threshold here, with the pure tone at 26.8 kilohertz, and a very strong correlation with the pure tone at 9.5 above this critical threshold. So we don't get a linear combination in terms of response between what you would get for the pure tones, but there is a clear separation. If you exceed some threshold here, what you get as a response of a network is actually very similar to what you get for the pure tone here. And below this threshold, you get something which is very similar for the pure tone at 26.8 kilohertz. So this is very similar to what you would expect as through a simulation, you cross a limit, a boundary between two basins of attraction, and the dynamic gets attracted to one of the two attractors corresponding to the pure tones. So this example I wanted to give you just as well. You see that microscopic models as Hopfield model can be actually useful to interpret in a conceptual way some experiments. But what I'm going to explain now is what happens when we go from the concept of discrete attractor to the one of continuous attractor. So here, instead of having a single point in this very high dimensional space, what we have is actually a set of points which actually builds or forms some kind of d-dimensional manifold. And the dimension of this manifold is actually much smaller. D is actually a small number compared to the number n of neurons, which is the dimension of a space of neural activity. So the example you see in this drawing here is the case of d equal 1. And we have a ring, which is a one-dimensional manifold, which is closed here. So what do I mean by continuous attractor? I mean that depending on the initial condition, the dynamics will end up onto this attractor. And there is an infinite number of points here, which are fixed points in the absence of noise. And the points in which the network will settle its activity depends on the initial condition. So the first paper actually proposing this kind of concept was written by Sushi Amari in 1977, and he actually gave an example of ring attractor. So what is important with this concept of ring attractor or continuous attractor is that the location of the point along with the attractor define a collective coordinate, x, which is a continuous variable in the case d equal 1, or could be a d-dimensional vector for higher dimension d. So you see that we can actually see this as a way to embed in a very high dimensional network, neural network, a continuous variable. So it's a way to memorize a continuous variable in a high-dimensional network. Okay, so let me try to be more precise and see how these ideas can actually help understand some experiments or some well-known facts. And I'm going to tell you about things you may already have heard about, place cells and hippocampal place cells. So place cells are actually cells or neurons which are found in the hippocampal regions CA1 and CA3. And their most important specificity is that they present spatially localized activity. So how do we understand that? So if an animal, typically a rodent here, is put in some arena, some environment, which is this round arena here, then the animal is going to move, maybe through just exploration, random exploration. And one particular place cell, so let's say the green place cell B here, will be very active when the rat is here in space and essentially silent outside of this region, which is called the place field of this particular place cell. Another place cell, which I call place cell number A, the orange one here, will have a place field located in this spot of the arena. So place cells were discovered first by O'Keefe and collaborators in the 70s. And John O'Keefe was rewarded with the Nobel Prize in 2014 for his discovery. So place cells have many important properties, and I don't have time to explain all of them, but let me make just a very brief list. First of all, they are stable in dark, so you don't need visual stimuli to have stable place cells. And they are stable also against limited changes of environment, maybe small changes in shape. They are retrieved when the animal is placed in the same environment after days. So if you train an animal in a new environment, then after some minutes, the place field will form. And if you remove the animal from the environment, put it back some days later, then the place field will be retrieved with a good accuracy. They depend on context, so that they don't code only for space, position in a two-dimensional space for the rodent, but they depend also on other sensory information like olfactory information, and also on the emotional state of the task to be performed by the animal. And something which is very important, I will come back to that and show you some experiments later. The firing sequences of place cells as the animal is moving, is doing some physical motion in space. So for instance, along this trajectory I'm showing here, cell B will fire before cell A. Then these sequences may be actually retrieved on much shorter timescales when the animal is immobile or is sleeping. And these compressed timescales actually give a proof or some evidence for the fact that this firing activity is supported by some network activity, and it's not just induced by some external inputs like visual stimuli. I'll come back to that later. Okay, so how can we actually build, let's say, the simplest model you can think of in order to get a continuous attractor having activities similar to these place cells here, which are experimentally measured? Then let us think about a one-dimensional environment, just to make drawing a little bit easier on the slides. So here is my environment, which is a one-dimensional corridor, and the rodent is actually moving from left to right along this corridor. So I will draw my place cells according to the place field position or place field centers they have. So for instance, the green cell corresponds to some position x2, which is small, or to the left of the environment, while the abscissor of the red place cell, x9, is actually large and correspond to a position which is on the right of the environment. And you see here the purple one somewhere in the middle. So how can we actually build a simple model where this place cell will have some activity dependent on the position of the animal? The model was proposed by Sodik and Sejnowski about 25 years ago. And here is how you can actually describe the model. So each cell will have an activity state, Ri, which corresponds to a firing rate, which is a positive or null variable. And the variation over time of Ri will correspond to some rest value here. You have some relaxation decay towards the rest value Ri equal to 0, a silent cell. But the cell is also receiving some inputs corresponding to, let's say, external driving force here, II, maybe external stimulus like visual stimulus, sensory stimulus, and also some recurrent current coming from the activity of the other cells, which are weighted by the synaptic coefficient Jij. So you see that depending on frequency Rj, then multiplied by Jij, then we sum over all the J's, which are all the other cells in the network, and there will be a nonlinear function here, typically a linear threshold function. That means if the argument here is below some threshold, then nothing will happen. If it is above some threshold, then the firing rate, there will be some positive contribution to the firing rate, and the Ri over dt will be positive. So Ri will increase over time. Now, how do we define this synaptic coefficient, which is the key ingredient of the model? So here the assumption, and we'll come back to that later, is that the synaptic coefficients are strong and positive if the distance between the place field centers corresponding to the two cells I and J is small. That means, for instance, between cell 2 and 4 here, since the place field centers are close to each other, then you have a positive interaction coefficient. And if the distance is large, then you have a negative coefficient corresponding to this long-range inhibitory term here. So for instance, the green and the red cell will be negatively interacting. So if you have short-range excitation and long-range inhibition, what is going to happen is that a bump of activity will create, which means that the cells which will be active together at the same time will code for positions which are close to each other, because they will strongly support their own activity by this short-range excitation. And on the opposite, they will inhibit the cells which are coding for positions which are further away. So depending on the position of the animal, which could be actually encoded in this very small input here, which is coming, maybe I will tell you what is the area of the brain which is responsible for sending signals, which depends on space. Then you will see this bump of activity, and as the rodent is moving, then this bump will actually move with the position of the rodent, which is very similar to what you see when you measure the activity of a single cell here and see a well-defined place field over space. Okay, so what are the main ingredients of the model? The active bump actually defines a collective coordinate x for the neural activity, which is the location of a peak of this bump. So even if the neurons are very noisy, so they are not in the Sodic synaptic model, but you will see models later on where they are very noisy. Since we have a lot of neurons creating this bump, then we have a robust encoding of this particular collective coordinate. The bump persists without any input. We don't need any sensory input to have a bump. It's just a property of this long-range inhibition and short-range excitation. But a weak input is sufficient to drive the bump and update its position according to the motion of the animal. And of course, this is straightforward to generalize to higher dimension. I mean, I did here the drawing in 1 dimension for laziness, but in fact, you can do that in 2 or 3 dimensions without any problem. I will show you some drawing in a while. So before I do that, let me mention that this concept of continuous attractor is not restricted to place cells in the hippocampus, but it was used by many people for many kinds of activities in the brain. First of all, I would say for the oculomotor neural integrator by Sung a long time ago. Also, in the context of spatial working memory in prefrontal cortex, for grid cells in the entorhinal cortex, which is another brain area compared to hippocampus, where you see also the activity of cells that depend very much on the position of the animal. Also for head direction cells, where, for instance, which is maybe the neatest application of the ring attractor concept put forward by Amari, where the activity of cells actually code for the angle of the head of the animal with respect to its body. And there were beautiful experimental illustration of that when people measured the activity in the ellipsoid body of flies, fruit flies, and also actually the activity that depended on the orientation of the head of the animal. So this is a direct proof of this concept of continuous attractor. So in 2 dimensions, as I said, it's very easy to generalize the idea that I just explained in 1 dimension. The only difference now is that the place field centers of a cell are vectors in 2D. They could be also in 3D. And the Gij should be a function of a distance between the place field centers here. And what you get is a bump of activity, which will actually have a peak corresponding to the position of the animal. Okay, so let me just say a little bit more about, since we have seen this model, how we can think maybe a little bit, it would be always very superficial, but what could be the neurobiological substrate of this model. And I will try to make also the connection with statistical physics now. So in the model I'm going to explain now, I will drop this idea of having continuous firing field. I will just consider model with some neurons, sigma I or Si, may have 0,1 activity. So you can say, for instance, you measure the activity of a neuron in a small time bin with a window of a few tenths of milliseconds, for instance. And if a neuron is silent, then its activity state will be 0. And if it emits at least one spike during this time window, then its activity state will be 1. Now we will build some interaction network between the neuron, and we will do that according to Hebbian learning prescription, which is summarized in a very superficial but simple way as fire together, wire together. So what does that mean? Take, for instance, two neurons, this green and orange neuron, and look at the position of the place fields in the space, physical space where the animal is moving. We can define some distance Rij between the centers of the place field. And you see immediately that if the distance is actually larger than the diameter of the place fields, which I assume to be more or less the same for all the neurons, then it's very unlikely that these two neurons will be active together at any time. While if the two place fields overlap, as the animal is actually in the overlapping region, then the two neurons will be activated together. And so that will have a tendency to strengthen the connection if there is any physical synapses connecting these two neurons. So we may imagine that the Gij after a learning phase connecting these two neurons will be a function of a distance, which will be positive and strong if the two neurons have place field centers which are close to each other, and maybe negative, and it's just a way to enforce some kind of well-defined activity states where all the neurons are not active together at large distances. So this is very similar to the Soddyk-Sosnowski model I just presented before. Okay, so this drawing was in the case of when you have two neurons, but of course in the hippocampus or in our neural networks model that we draw on the paper in our computer, there are many more than two neurons. And so you can imagine that you will end up after a learning phase by drawing some kind of network which actually will represent the topology of the network of place fields here. And we put a connection, strong connection between neurons with overlapping place field here. And if I didn't make any mistake, this network of connections correspond to the topology of a place field location here, where you have a connection between overlapping place fields, and no connection if they don't overlap. So this drawing here, I mean, we should be a little bit careful about the interpretation. The notion of place field in physical space is actually well defined, but we have no idea about the physical position of the neurons in the hippocampus, in the neural network in the brain. Of course, there shouldn't be any simple mapping as the one I have shown. What we would expect is something very similar to that the position of the neurons in the hippocampus have nothing to do with the relative position of their corresponding place fields in physical space. And this is important to keep this in mind, because when people do experiments, what they do is that actually they put some electrodes, or they may have some optical recording, but they will see a limited portion of the hippocampus. So they will see the activity of these neurons here, close to the tip. Close to the tip of the electrode here. And of course, due to this random mapping here, that corresponds to place fields which may be actually very far away in physical space. Okay, so suppose we have in this network now, the Gij matrix is well defined. So what is going to be the distribution of neural activity configuration? So what I will do here is that we have a very, I would say, oversimplified model, but which will allow me to do some connection with statistical physics. So I need to define first some dynamical rules on the n-dimensional hypercube Since each neuron can have 0, 1 activity, I have n neurons, so that means I have 2 to the n possible configurations of activity. So how do I move from one to the other as time is going on? So suppose I am on the left activity configuration here, where neuron number I, sigma I, is actually in the 0 activity state. So sigma I, that means neuron I is actually silent in this particular time being. So what I will define is some specific dynamical updating rule, which will move to sigma I equal to 0, from sigma I equal to 0 to sigma I equal 1 with some rate, which is probability per unit of time, R. And it will move back from this right configuration to the left one with probability per unit of time 1 over R. So R here is a positive number. And the other activity configuration for very small time interval are supposed to be constant. So sigma 1 up to sigma n, except sigma I cannot move, cannot change value. So how do I define R? This is given by the formula that you see here on the bottom left of the slide. So log R is going to be a positive or negative number. So R is between 1 and 0, and between 0 and infinity. And there are two contributions you should see here. So the most important one is the one with the summation here. What I do is that I will sum the activity states of all the other neurons in the network, J. So sigma J is equal to 0 and 1. So I consider only the active ones. And the active one will be weighted by the interaction coefficient, which is the function of the distance between the place field centers of the place cell I and J. And this term will be a positive or a negative number. I will compare it to some threshold theta here. And I will get some number. And this number will be divided by some variable t, which I'll call it neuron noise, which is similar, as you will see in a couple of seconds, to the physical temperature in statistical physics. So you see, if t is equal to 0, I will get a very strongly positive or very strongly negative number for log R. So that means my rate R will be either very large and positive or very close to 0. If t is actually large, then I get log R very close to 0. That means R very close to 1. And there will be essentially no distinction between the left update and the right update, because R and 1 over R are very similar in values. So what is the idea of this definition, behind this definition? So if I look at what is going on in a time window of a few tenths of milliseconds, maybe 10 milliseconds, then my neuron, my postsynaptic neuron I, is going to integrate all the presynaptic inputs from the other neuron J through some, and weighting them with some synaptic coefficient Jij. And depending on whether this input current is going to be above some threshold or not, then the postsynaptic neuron I will going to emit a spike or not. This is what you have learned from biophysics of neurons 101, for instance, the Hodgkin-Huxley model. So obviously what I'm describing now is an oversimplified version of Hodgkin-Huxley model. This is much simpler, but it captures the main ingredients that you would expect for a real neuron, that is summation of input from other neurons, and then a nonlinearity phenomenon which will decide whether a spike or not is emitted. Okay, so you know from your knowledge in statistical physics that if you have a model where these dynamical rules is actually followed, obeyed, and the neuron I is selected randomly over time, and then updated according to this rate R, then what is going to happen is that at sufficiently long time, there will be a stationary distribution for the neural activity configuration, which is going to be defined by the Gibbs measure here, which is shown here. So the joint probability of all the end states of neurons will be the exponential of some minus energy, formal energy, which is given by the terms here, sum over all pairs of neuron I and J of the sigma j weighted by the coefficient of interaction Jij here, minus theta sum over I sigma I. So theta plays the role of a negative magnetic field, and T plays here exactly the role you would expect from temperature in statistical physics. So essentially what you get here is what you would expect for the joint distribution of activity of an Ising model with a global field here, theta, which regulates the average magnetization, and interaction coefficient here, which depends on the distance in physical space attached to the different neurons, sigma, sigma j. So the connection with statistical physics is here very clear, and this is actually why I built this model. And it's actually very similar to a model which was proposed a long time ago in the context of the liquid vapor transition by Leibovitz and Penrose at the end of the 60s, or in the middle 60s. And what Leibovitz and Penrose proposed was a lattice gas model for the liquid vapor transition. So imagine, for instance, you have a, let's say, a two-dimensional, three-dimensional, it doesn't matter, it's just a question of simplicity for the drawing here on the slide. And on this grid, you have sites, and the sites can be occupied by one particle of liquid at most. So we assume that the repulsion at short distances is so strong that no two particles can occupy the same spot. So the activity state, which is actually an occupancy state here, occupancy number, Si, is equal to 1 if there is a particle of liquid, a particle of matter on one side, I, and 0 otherwise, if the site is empty. Okay, so now what is going to be the interaction between the different sites? So you can imagine some kind of discretized version of a Lennard-Jones potential. So at short distances, you have a weak attraction between the particles. So Jij is going to be positive at weak distance, and it's going to be 0 at large distances, like you would expect that for a Lennard-Jones potential. And so the energy is going to be minus the sum of all pairs Ij of Jij, Si, Hj. And the Boltzmann distribution of the particle occupancy numbers at temperature T, I put here the Boltzmann constant K equal to 1, is given by this formula here, which is the Gibbs measure. So how do I regulate here the number of particles? Well, this is fixed, right? So I don't need any external field which is acting here simply because sigma I, summa I or sigma I or summa I or Si is a fixed number. So that means that it doesn't play any role. If I have some kind of grand canonical ensemble where some particle can be put in and removed from my system, then I would need some kind of chemical potential, and theta would play the role of a chemical potential, which is also a magnetic field in the language of magnetic models, ferromagnetic model. So what can we say about this model? So that was solved in the case of very long-range interaction by Leibovitz and Penrose. And what you get is actually a phase diagram which is similar to the one drawn at the bottom of the slide. So at very high temperature, if you look at the profile of density of particles of the space, then it's uniform. So you have a vapor phase which is homogeneous of a space. But at low temperature, below some critical temperature, you get a separation, a phase separation between two different phases. One is the liquid phase with very high density of liquid, and that corresponds to this dark region here, which is a droplet of liquid, which is surrounded by a very low density phase, which is just a vapor. Okay, so you get a coexistence between these two phases here, which is separated by a first order phase transition. Okay, so if we are at low temperature, which correspond to low neural noise in our continuous attractor model, I'll come back to that later. Then, of course, since the model is totally translationally invariant, you see there is no difference between having this high density liquid region here or somewhere else in space. Then this bump, this very strong bump of high density of liquid will actually diffuse over time, and it can occupy any position in space. So this is very similar to the definition of these collective coordinates I mentioned before. The location of a center of mass of the bump defines a collective coordinates in our n-dimensional space of configurations of occupancy numbers here. So we see a very strong analogy between the neural network model I discussed before and this vapor liquid model I have just introduced. And we can actually build a dictionary that is shown here. On the left, you see all the terms corresponding to the neuroscience problem or issue we were discussing. And on the right, all the statistical physics terms. So for instance, the neurons can be active or silent in a time in t, which correspond to a site which can be occupied or empty at the same time t. The local excitatory connection corresponds to local attractive interaction between two particles which are close to each other in space. And the long-range inhibition, which fixes the population activity, corresponds to having a fixed total number of particles, which can be the atoms or the molecules in my system. The location of the center xi of place field of neuron I is actually the location xi of site I in space. And this is actually where the distinction between the physical model on the right and the neuroscience model on the left is actually interesting. As I told you, here there is a connection, an obvious connection between the position xi on the site in physical space, okay, and on the grid. It's actually the same object. There are no two distinct objects. While in the model of neurons I had, we had completely distinct values for the position xi of the center of the place field and the position of the neurons in the hippocampus, which actually does not matter very much to the model here. I'll come back to that later because it makes the neuroscience model more rich than the physical model and so on. Now, the droplet of liquid I had in the physical model correspond to the bump of neural activity in the neuroscience model. The mean activity of the neuron coding for the position x corresponds to the density of particle in x in physical space, and the neural noise I introduced in the rate r corresponds to the temperature in the Gibbs measure. Okay, so I will use this analogy very much to make some analytical calculation in a while, so please keep that in mind. Okay, so what we have done so far is that we have introduced a model which seems actually a reasonable model when we have a single continuous attractor. We know how to do that, and we have seen that it's actually very similar to all models introduced in the 60s in statistical physics. But now let's try to move to something which is more interesting from a neuroscience model point of view, which is how to embed multiple continuous attractors in a single neural network. In fact, beautiful experiments have shown that the single hippocampus, the hippocampus of a rat, can memorize many different environments. It is obvious since the animal in its life has to do that. It has to know many environments and to be able to navigate in this environment. But this was shown in an experiment, in particular the one done by Charlotte Alme and collaborators in 2014, where these people were able to record the activity of place cells in the hippocampus of the same rat in 11 different rooms, and see that actually the activity of these cells were actually specific to each room in the set of 11 rooms. So that means we can actually make some drawing which correspond to the central part of the slide, where a single network here with some specific interaction Gij between the neurons should be able to accommodate at least 11, or let's say some undefined number, unlimited number of attractors in the very high n-dimensional space. So how can we do that? How can we choose the Gij matrix to do that? And how can we actually move along this single attractor depending on the weak inputs, which could be sensory inputs, which define the collective coordinates here? How can we jump onto another attractor depending on the sensory or the contextual information, and then describe another collective coordinates here? So this issue is actually not purely academic, and I will discuss that tomorrow in my second lecture. But I just want to give you a glimpse of why this is important in the animal's life. In fact, the idea is that even very different representation of the same environment may, in some occasion, have to be recalled on very short time scales. So you can think of an animal which is actually, for instance, exploring an environment in search of food, is actually eating something in some place, some spot in the environment. So this is contextual, let's say, state number one. But then a predator is arriving, and then the animal is not looking for food anymore, but it's looking for shelter, which is contextual situation number two. And you see, it may be actually very important to code in context one for the location of the food, but in context two for the location of a shelter, and be able actually to join this shelter and reach this shelter very, very fast. And in fact, this situation was shown in a beautiful experiment by Kahneman and Fenton some years ago, 10 years ago. And actually, different representation can be loaded in the hippocampus depending on the context on very short time scales. And I will be interested tomorrow in trying to understand how this can be done from an analytical point of view in the models, but also how this can be seen in recordings of activity in real experiments. So this will be part of my lecture 2 tomorrow. So let's come back now to lecture 1 and see how can we change actually the model we have seen, which is able to embed one continuous attractor in a network, into a model which is able to embed more than one continuous attractor. So we'll see two ways of doing that. And the first way was proposed by Samsonovich and McNaughton about 25 years ago. And what they proposed was an extension of the Hoffman model. So the idea is actually very nice and simple at the same time. So we know how to embed one continuous attractor corresponding to environment 1. And we did that, as I've shown you, by building a synaptic connectivity matrix, which positive strong coefficients for overlapping place fields, or let's say for neurons having overlapping place fields, and let's say weakly negative coefficients or interaction coefficients for non-overlapping place fields. Okay, so that means in environment 1, we have defined a synaptic connectivity matrix, Gij1, which depends on the position of the place field in this environment. Now, if the animal is actually exploring another environment, then the same neuron may have place fields at different positions in this new environment, which is called a phenomenon which is called remapping. So for instance, the green and the blue neurons, which were far away in terms of place field in environment 1, may be actually overlapping in environment 2. So we may define a new synaptic connectivity matrix here in this environment, which depends on the relative position of the place field. And so on. You can do exactly the same thing in environment 3 and so on. Now, a simple assumption is that as the animal is actually exploring all this environment, then maybe some additive prescription is going on. And what the animal is learning is the superimposition of all these matrices of interaction. Gij, which is the sum of Gij1 plus Gij2 plus Gij3 and so on. Okay, of course, there are a lot of assumptions here in terms of how this could be implemented with biologically plausible phenomena or mechanism. I'm not going to discuss that. I'm just assuming this could be a plausible model, or at least a simple model. Okay, so what is going to happen if you do that? So let me show you some results here of a Monte Carlo simulation. So how does that work? Well, what I'm doing is actually, I'm just following this prescription here. I'm using exactly this dynamical rule here. Well, now, instead of having a single environment, I have a Gij matrix, which is a superimposition of many environments. So many being 3 in the simulation I'm going to explain. So this is the model here, where I have 90 by 90 neurons on a 2-dimensional grid, so about 8,000 neurons. And I have 3 maps in 2 dimensions, so 3 environments in 2 dimensions. And the connectivity matrix is just a superimposition of 3 different connectivity matrices, where each one depends on the position of a place in that particular environment. So, and then I will just simulate the dynamics with the updating rates R I have shown before. And so with the Monte Carlo simulation. So at any time, I will have a 8,100 dimensional vector of activity with all 0 and 1s for components. And I will represent this vector, this single vector of activity at any time t in 3 different ways. So how do I do that? I will look at this vector first in the red environment, which is the environment number 1. And I will put a red dot at the center of a place field of the neurons which are active, so which are equal to 1 at this particular time in the red environment. Okay? So you may think that you have 8,000 neurons. They have place field covering the whole space here, which is this square here. And when they are active, I put a red dot. The same neurons are active, obviously, because the activity state do not depend on a particular environment. It's a way of representing the activity state. I will, in the second environment, I will put a blue dot at the center of the place fields. And also in the green environment, here a blue dot. So I start with an initial condition where I create artificially a bump of activity in the red environment. That is, all the neurons which code for this position here, which is the center of the environment, I put them equal to 1, and all the other neurons are silent. So all the red dots here are located around the center of the environment here. And of course, See, I choose completely random position when I do the remapping in the other environment. Then the position here are completely random and scattered over space in the blue and green environment. The last panel here is showing minus the energy corresponding to the ferromagnetic energy. So minus the sum of the J and I of Jij sigma I or sigma J, with the Jij which correspond to the red, the blue, and the green environment. While obviously the full Monte Carlo simulation is done only with the matrix, which is the sum of the three matrices, right? As I explained with the Samsonovich and McNaughton. So let me show you the simulation. So the simulation is done at a fine temperature, and you see that the red bump is actually very noisy, but still the place, the center of mass is well defined. And you see actually that the bump of activity corresponds to a well-defined position in the red environment, while the activity is completely scattered all over the place in the other environments. Okay, so now as the activity, as time is going on, then the activity is actually moving in space, but still we have a well-defined bump. But now you see at some point, the activity will be delocalized in the red environment and become concentrated in the blue one, as now. And we see some jumps from one environment to another one. And at the end of the simulation, we see a bump of activity which is concentrating in the blue one and which is delocalized in the red one and the green one. So we see that we have a model which is able actually to have a coherent activity in one of the three environments, not always the same. It spontaneously jumps from one environment to the other one. And it's coherent because the neurons which are active at any time in one actually correspond to a single position in one of the three environments. You see, that corresponds to the center of mass here in the blue one. And we see some crossing here, which is just due to the random noise in the Monte Carlo dynamics. Okay, so just to be to summarize, what we had was a model where we have n neurons, L manifolds, or let's say I call them L maps or L environments, if you prefer, which are d-dimensional simulation with d-dimensional manifolds. So in most of the cases, d is equal to 1, 2, or 3. And the main ingredient is that each neuron I was supposed to have a place field in manifold mu, which was centered in some position xi mu, which I chose in a completely random way. And the couplings were given by the sum of the synaptic interaction matrices, Jij mu, where each Jij mu is a function of the distance between xi mu and xj mu in the environment mu. And f is a decreasing function of the distance, which go from being positive to negative as the distance is increasing. So it's just an extension of the d-dimensional case of the Rafi model that you can see as the case d equal to 0, which corresponds to discrete attractors. Okay, so what can we say about the properties here of this model? So I've shown some Monte Carlo simulation, but can we be more precise from the analytical point of view? Can we actually build the phase diagram of this model? So the answer is yes. And essentially what we have to do is to study the properties of the Gibbs measure, which I have written here on the top of the slide, which is just a ferromagnetic model in each environment. But what makes this model complex is that we have a superimposition of different ferromagnetic matrices which are not compatible with each other. Because two neurons which actually interact together with the positive coupling, which are close to each other in environment mu equal 1, may be actually far away and have a negative contribution in environment 2. So that creates some kind of frustration. So the model we have at the end is very similar to a spin glass model. So a lot of technologies from an analytical point of view have been invented in the 70s and the 80s to deal with these models. And I will not make calculation, do a calculation in details, but I just want to give the main ingredients very briefly. And if you are interested, of course, I could answer your question in more details at the end of the lecture. So how do we do? I will assume that in one of the environment, actually, we have a bump-like activity, which is a very nice regular profile of activity, which corresponds to a well-defined collective coordinate x. So let me assume without loss of generality that this happens in an environment mu equal 1. So the activity, the main activity of a neuron rho will be a rho of x, and x will correspond to the collective coordinate, or if you prefer the coordinate of the position of the animal in this environment. Then the other environments, mu equal 2, 3, and so on up to L, they will actually in some way they will create some kind of perturbation to this nice smooth activity profile in the environment mu equal 1. And that is due to all the contribution J2, J3, and so on up to JL, where J mu are the connectivity matrices due to environment mu. So they will actually create some kind of interference with the environment 1, which lead to this spin glass frustration effect. So despite the presence of this quench disorder, which is actually fixed in the connectivity matrix and doesn't change over the simulation time, we will make some hypothesis, concentration hypothesis of the free energy, which depends on the profile of density profile rho of x. And the J mu larger than 1 actually act as some quench disorder. I will assume that when n goes to infinity, so for very large population of neurons, then the probability density of the different rho of x, the density profiles, will actually become very highly concentrated around a single rho of x. Or if you prefer, the free energy, which is a function of rho of x, will have a single minimum. And since the free energy is actually an extensive function of n, proportional to n, then only one profile rho of x will dominate in the large n limit. So since this density is going to be unique, we can compute the average density, the average free energy, by actually averaging over all the interaction matrices J mu larger than 1. We do that by computing. This is a quite tough calculation, but we use the replica method to do that. We'll compute the nth moment of the partition function, and that we can do for m, which is an integer number, m equal 1, 2, 3, 4, and so on. Then we will do some analytical continuation of this result of the free energy we find as a function of real m, and send m to 0 to compute the average of the log of the partition function, which is the average of the free energy. So I'm skipping a lot of very interesting and hard technical details here. I just want to give let's say the overview, a very broad sketch of the technique. So we end up with a theory where we have different order parameters. One will be rho of x, which is the profile of activity in the first environment. So what we do is that actually, so this is the definition of rho of x. We look at all the neurons I, and we will actually label the neurons according to the position of their place field in the first environment, mu equal 1. And we compute the average activity of neurons whose positions are somewhere in between x, around x, maybe within some epsilon, but epsilon will be sent to 0 eventually. And we define the average density of these neurons here, which we define rho of x. We define as rho of x. So it's a number between 0 and 1, which depends on the continuous variable x. But since we have quench interaction coming from the other environment, we need another parameter, which is coming out from the replica calculation, which is the Edwards-Anderson overlap, which measures the spatial heterogeneities in the activity. So Q will be just the square of the magnetization of the different neurons. So if we had no quench disorder, so a single environment, then Q will be simply the integral over x of rho of x squared. But actually, it's larger than that due to the other interactions. And the difference is actually measuring the intensity of frustration, or let's say the consequence of the frustration in the network. So just to be a little bit more physical here, if I look at some neuron I, this neuron at any time during the Monte Carlo simulation or at equilibrium, for any configuration at equilibrium from the Gibbs measure, is actually subject to some effective field, Hi, which is the sum of two very different contributions. One is what I would call the coherent contribution, which corresponds to the activity of the other neurons in the same environment where the bump of activity is present. So this is the sum of the J of Jij1 Si, where 1 is the index of the environment. And if I consider, let's say, the position of this neuron to have a place field center in x equal to 0, just for reference here, then you see that this contribution here will depend on the other neurons. J will vary with the coordinate of the other neurons, x. So J can be translated into x. the position of the place field of neuron J. And it will be something which decays very quickly with X. Essentially 0 if you are outside of a region which corresponds to the side of a bump, and which is strong and positive otherwise. So this is very smooth and regular with X. But then the problem is you have the contribution coming from the other environment. So the same neurons, because we have a single neural network, they actually contribute in a non-coherent way due to the interaction corresponding to the other environments which are stored in the network. And they will contribute some Gaussian random variable. And the intensity of these Gaussian random variables depends on the overlap Q. It's a non-trivial function of Q, which I don't want to write here, but you can have a look at the papers and ask me questions if you want later at the end of the lecture. And it's proportional to the ratio of the number of environment divided by the size of the network, the number of neurons, which I call alpha. So if we have very few other environments and we have a very large network, alpha is very small, and this intensity here is actually quite negligible. And we are essentially in the case of a single environment. Otherwise, if alpha is large, we get a lot of corruption, a lot of noise, which is corrupting actually this very nice smooth signal here. So we see actually some kind of battle between this nice smooth signal here, which is stabilizing the bump in the nice in the right environment, and this noise here, which is actually destabilizing the bump. And who is going to win depends on the value of alpha, which is the ratio of the number of environments over the size of the network and the value of temperature. So here is the phase diagram, which is made of essentially 3 different regions. If we are at low temperature, so small neural noise, and small structural noise, like a small number of environments stored in the network, then we have a picture which is very similar to the one of a single environment with a nice bump of activity, which corresponds to a nice, well-defined coordinate in one environment, and which is essentially, let's say, random and smooth in the other environment here, flat in the other environment. And that corresponds to a rho of X, which is different from the average activity, so it depends on X, and Q, which is larger than X squared. So this is the bump memory state. If we are in a region at low noise, low temperature, but large number of environments, then the network is actually not able to recover any environment. There are too much or too many interference between the different environments. We want to store too many environments in the same connectivity matrix, and the network cannot handle that. So what we get is that there is no bump in any environment, and we get a spin glass phase, where the profile is actually rough in all the environments. And we have also a high temperature phase, very similar to the one in the Lebowitz-Penrose model. If the temperature is actually too high, then actually there is no bump in any environment. So it's a paramagnetic phase, which is not very interesting. So the main theoretical result, which is coming out from this phase diagram, is that a recurrent neural network with n neurons can embed an extensive number of d-dimensional manifold as long as L, the number of manifold, is smaller than n, the number of neurons, times some critical threshold, which is a function of t. This result was first obtained by Batali and Trebas in a continuous neuron setting in '98, and we re-derived it for 0-1 neurons more recently. So that looks very nice because it means that you can put a lot of environment in this network, but actually this is some kind of, let's say, misleading statement, because there is a major problem with this theory of continuous attractor neural network. The attractors are not flat. In fact, the bump of activity, as I said, can be found in any network, but due to the other interaction, it is trapped in some preferred position. As the bump of activity is moved along, let's say, environment number 1, then they will see that there are some positions where they can be trapped and other positions which are very unlikely. So that means there is a spatial resolution, which is not controlled by anything but the other random interference connection. So actually, we don't have a nice representation of the first environment or any environment, but we have some kind of very distorted representation with only a few points which are allowed. So there is a very important question of spatial resolution versus capacity trade-off here. And the analytical calculation I've just sketched here do not say much about that. So how can we actually embed in a controlled way many different attractors, such a way that the spatial resolution is good? We don't have any a few spots where the bump can lie, but it can be anywhere in the environment, so that it can really store some specific position of the animal. So what I propose as a mechanism is something we have done recently, is actually to turn this notion of continuous attractor into a notion of quasi-continuous attractor. So I would like to memorize discrete approximation of multiple continuous attractors in a single network. And by discrete, I mean that we have, if you look, for instance, at this very high dimensional space of the activity of a population network, of a neural population, I will look at one attractor here. I will memorize many positions which correspond to this red cross along this attractor here. And the distance between any two positions, epsilon, I mean contiguous position, nearby position, will be very small, which means that actually the bump can be somewhat, it can lie here or somewhat very close here. That means even if epsilon is finite, it's not equal to 0, in practice it's much smaller than the size of the bump, and I will have a very good and excellent approximation of a continuous attractor with a large set of a very nearby, a very close position of discrete attractors. So the question is, how can I control epsilon and make it as small as possible? And then when I do that, second question is, how much do I lose in terms of my capacity? The smaller epsilon, so the finer the description in terms of space, then the smaller should be the number of attractors I'm able to embed in my network. So what is the relationship between epsilon and the capacity of a network? Okay, so let's try to answer these two questions. First, how can I control epsilon? So I will do that in the following way, which is actually reminiscent of Samsonovich-McNaughton model, except that now I will actually draw some data and not some a priori interaction matrix. So I will still start from a network of n neurons, I running from 1 to n, L manifolds mu from 1 to L of dimension d. So each neuron I has a place field in manifold mu, which is centered around xi mu, which I'm assuming to be a random vector here. So this is absolutely identical to the Samsonovich-McNaughton model. Now things are changing. I will define some specific points on each attractor. I will actually define P of them, which I call anchoring points, which are points which are able to anchor, to pin the bump of activity of my network. So I will define these points xm with m running from 1 to p for each attractor mu. And you see, if you assume, for instance, your environment is a square of unit side. So the width is, let's say, 1. It's just a definition of the width, right? You draw randomly p points uniformly at random in this square. What you have is that the distance, typical distance between two neighboring points is going to be as 1 over square root of p. Now, if you do that in dimension d, or d equals 1 or 3 or 2 as I just done, then the typical distance between neighboring points will be 1 over p to the 1 over d. So p to the minus 1 over d. So as we increase p, then we'll have a smaller and smaller values for epsilon. So that's how we will control our numerical accuracy on space. Now I will define some data configuration, that is activity configuration of my network in the following way. Each neuron I in manifold mu and anchoring m, and our anchoring point m, will have an activity 0, 1, which I call sigma I mu m, defined as some function of the distance between the anchoring point and the place field center of neuron I in this manifold. And this function here will be, let's say, 1 if the distance is smaller than some cutoff, and 0 otherwise. Okay, so I give you some example in the bottom drawing of the slide. So you see here the case of 5 neurons, which correspond to 5 different colors, 2 different spaces, 2 different environments, the left and the right here, left and right, in dimension 2, and there are 2 unit squares. And you will see 3 anchoring points. So each blob here, each disk here corresponds to the place field of each neuron. So for instance, this blue neuron here has some place field centered here in environment 1 and here in environment 2. The red one, since we have the periodic boundary condition, has some place field centered here in environment 1 and here in the environment 2. Now you consider one of the anchoring points. So let's say, for instance, this square here, this purple square here. So what are the neurons which overlap with this neuron, with this anchoring point here? Well, you have the yellow neuron, the green one, and also the light blue ones. So they will have one activity, and the other one will have 0 activity. And this is exactly what you see here. Oh, sorry, I made a mistake for the light blue here. It's not overlapping because it's an here. So you see 2 ones here and 3 zeros in this column. Now, if you take another anchoring point, for instance, in the second environment, so for instance, the orange star, you see it overlaps with the red and the light blue, and that corresponds to the 2 neurons which are active on the other side. Okay, so I hope you understand now how I create activity configurations in my model. And what I would like to do is actually to build a network which is able to store this activity configuration. So each anchoring point define an activity configuration which should be a fixed point of the dynamics, or a discrete attractor of the dynamics. So which dynamics I'm considering here? It's a very simple recurrent neural network dynamics, where I start at any time t, I have a configuration of my n neurons, which are 0 ones. I will simply build the current, or let's say the input onto neuron I, postsynaptic neuron I, as a sum of a j of wij sigma j. And the activity here of neuron I at time t plus 1 will be 1 if the argument of s is larger than 0, and it will be 0 if it's smaller than 0. You can insert some temperature, so instead of having a 0, 1 step function, you can have some kind of hyperbolic tangent function, for instance, with some finite slope equal to 1 over temperature. And so my condition is that I'm asking that the data here, this sigma I mu m, are fixed points of the dynamics. And I will do that, I will impose this condition using a technique which is well known in machine learning, which is called support vector machine. Essentially, I will look for the best coupling matrix, which is maximizing the minimal margin. So which is creating this maximal hard margin between the activity point, I mean the data point, and the activity hyperplane, the decision hyperplane corresponding to each neuron. So I'm not going to explain this in details, but what you can see here is that fixed I, you see you have a sum of a j of wij sigma j. So you can see wj as a vector. So it's a dot product between the vector wj and the vector of activity sigma j, where you take all neurons but neuron I. So the vector w defines a hyperplane which is orthogonal to w, and whether the vector sigma is on one side or on the other side of the hyperplane, then the argument here will be positive or negative, and sigma I will be 1 or 0. So what you want to find is that for all the neurons, all the patterns of activity such that sigma I is 1, you want to put all the data points on this side of the hyperplanes, and for all the patterns such that sigma is equal to 0, you want to have the data points on the other side, and they should be as far as possible from this thing here, in order to tolerate some noise, to be robust to a little bit of mistakes, maybe in the activity patterns, or maybe to some noise if you put a finite temperature. And that corresponds to the maximal hard margin condition, which is at the basis of the idea of support vector machine. So here we have a support vector machine with auto-sensitive mapping. So we don't associate a vector of inputs to an output, but a vector of inputs to itself. So it's a way to do unsupervised learning of the manifold. So let's do that. So here we have a single environment in 2 dimensions in square. We have many anchoring points which correspond to the red crosses here, which I've drawn randomly in the space, in the square. And we have also a large number of neurons, which I think was equal to 1,000 in simulation. So we learn the best W, which maximizes this thing here. So how do we understand this condition? Well, we take this argument here. If it's positive, and we want the output to be positive, then you see that 2 sigma minus 1 will be 2 times 1 minus 1 should be 1. If we want the argument to be 0, then we'll multiply by minus 1, which is twice 0 minus 1. So you see that what we want is actually that this product here should be always positive, and we want this to be as positive as possible. So this product here depends on the manifold mu, the anchoring point M, and the neuron I. So we take the minimal value over all I, mu, and M, and we maximize this minimal value over W. So we take the worst neuron for the worst pattern of activity in the worst manifold, and we weight this worst case as good as possible by choosing the best W to do that. That can be done in polynomial time with, since this is actually a convex target function, objective function, and support vector machine packages do that very efficiently. So we do that here, and I'm showing you the result then when we do a Monte Carlo simulation at finite temperature, which corresponds to using these dynamics here with a hyperbolic tangent with a finite slope. And you see we start from this initial condition where you have a nice bump, and you see that the activity is random, but still the bump is really well formed. So so this looks like very much continuous attractor. Formally, it's not, because we have a set of discrete attractors. But since these discrete attractors are very close to each other, we cannot make a distinction with the noise due to the noise with the continuous attractor. So it's a very efficient, practical way of embedding a quasi-continuous attractor. So we can do better, or let's say more complicated, when now we have two environments. And so we do exactly the same thing. So one part of the data points would be drawn from the first manifold, the other part from the second manifold. And you will see the simulation. So we start with the bump of activity in the first manifold. And of course, we have periodic boundary condition here to make simulation simpler. So you see the bump of activity is very clear in the first in the square here, while it's completely random in the second one. But at some point, you will see that the bump of activity will materialize in the second square. So it's always in the first one here, and then we will change. We have to be a bit patient. And you see that there is a very dense activity in the second square at some point, which means that there was a jump from one attractor to the other one. Now here it's dense in the right square, right? While it's more or less uniform and random in the first one. So we see that with this prescription, this learning rule, which is completely different from the Samsonovich-McNaughton one, we can control actually the accuracy, the spatial accuracy, by changing the number of anchoring points. And we can have a model, which is able to embed many different manifolds. So actually, what does many mean? Because here I've just shown a simulation for two. So in order to understand that, we can use Gardner statistical mechanics framework in the space of interaction. So I won't make any introduction to this framework, but I will be very happy to answer questions and give you proper references. So Gardner wrote a very influential paper at the end of the 80s, where she was the first one to do actually statistical mechanics in the space of interaction to understand what could be the capacity of neural networks. So from a purely formal point of view, we have a set of inequalities here, which is exactly the argument of the function I've shown before here. And I want, in the worst case, to be this kappa stability to be equal to 0. It should be positive. So we have all these inequalities that should be satisfied at the same time. So if we have few manifolds, then of course, there are many ways of choosing the W matrix to satisfy all the inequalities. And that corresponds to, if you think here as the square of the set of all possible matrices W, that corresponds to a subset here, which is this blue subset here, which is large. As you increase the number of manifolds, you have more and more inequalities, and the subset shrinks. That corresponds to the orange one. And if you have very close to the maximal number of manifolds you can embed, you will be in the red situation, where actually the whole set will shrink to a single point. And if you put one more manifold, then there will be no point left. That means you have no solution. You are above the maximal capacity of your network. So what we want to compute is actually the size of this space here of solution, or let's say the logarithm of this volume of solution, which as a function of L over N, the number of manifolds over the number of neurons, will decrease here. That's a log of the volume, and will go to minus infinity. That means the volume goes to 0. at the critical threshold alpha c, which depends obviously on the number of anchoring points p. As we have more anchoring points, we have more constraints, so that means alpha c should be smaller. And the big question is how fast is the decay of alpha c with p, or more precisely, if you want in a different way, or more intuitively, I should say, what is how fast does the capacity decay with the spatial accuracy you require on each manifold? When you have more manifolds, or if you want to store a manifold with more accuracy, then the number of manifolds you will be able to store will decay. And what is the connection between the accuracy and the number? Okay, so this analytical calculation can be done exactly for small p. By small p, I mean 1 to up to 10. Actually, we were able to do that. We couldn't do it analytically for any p because we have actually a quadratic optimization problem to be solved, which is quite tough. But we have an analytical approximation which we believe to be exact when p is large. And I want to show that on the connection with random matrix theory. Okay, so let me show here the result of a capacity alpha c of p as a function of p here, which is the number of anchoring points. So we start with p equal 1. That means on each manifold, we have a single point. So here, if we have a single point, the very notion of manifold doesn't make any sense. I mean, it doesn't matter. Just draw around your point in space, and that corresponds exactly to what Elizabeth Gardner did in 1988. There is no meaningful induced correlation between the patterns here of activity because you have a single pattern for each manifold. And she had computed this capacity, and in fact, we found it back when we did the calculation. Now, what becomes interesting is that what happens when you increase speed, so you have more points. So if you have more points, let's say 2 points, now you see what is going to happen. If the 2 points actually are far away from each other on the manifold, then the interaction will be small. And essentially, when you have 2 constraints induced by these 2 patterns, you will simply decrease the capacity by a factor 2. And this is essentially what is going on. As you put more and more points, then of course, now these points are closer and closer to each other. So the constraint they induce, I mean, the inequality they induce on the W matrix, on the synaptic interaction matrix, are more and more similar. So actually, the factor by which you decrease the volume of a space in the W space is actually less than P, because the more patterns you have, the more similar they are, and the more similar are the constraints. You know, at the end, if you have a very large number of patterns, you don't introduce very effectively new constraints. So the capacity should decrease very slowly. And in fact, we see that when we do numerics with support vector machine algorithms. So the question is, can we characterize here analytically this decay, which should be much smaller than 1 over P? So I will not show again the technical details of calculation, which would require a whole lecture by itself, but just give you the main ingredient. And the main ingredient is that it's actually very much connected with the spectral properties of a quite interesting matrix, which is called a Euclidean random matrix. So Euclidean random matrices were introduced by Mézard, Parisi, and C 20 years ago. And the idea is the following. It's a very simple way of defining random matrices, but the analysis of these random matrices is quite tough. Imagine you have a space. So let's say here a box, a unit square, and you basically put randomly endpoints here. Randomly with maybe some measure, but otherwise uniformly at random. So you do that, and then once these points are drawn, you will beat your matrix. And in the following way, what you do is that you pick up any pairs of points, I and j, and we will build, and we will define the entry of the matrix Cij as a function of the distance between the 2 points, xi and xj, in this space. So you see, it's an ensemble where the different entries of the matrix are actually correlated between each other, because from n points, you build n square coefficients, so then they cannot be independent. So it's an ensemble which is more complex than, for instance, the Gaussian orthogonal ensemble or Gaussian unitary ensemble. And so Cij will be a function of the distance xi minus xj, and this function is some deterministic function, typically decreasing with the distance. So if you do that, and you draw in a finite box many points, so when n goes to infinity, actually, if you do that uniformly at random, you have a high density regime of your Euclidean random matrix, which is quite simple to deal with. The eigenmodes are Fourier plane waves, simply because you are simply essentially putting your points as if they were, perfectly put on a uniform grid. So as n goes to infinity, the large eigenvalue are closer and closer to what you would expect from Fourier analysis. What is interesting here, remember, we have a single hippocampus, but we have L different manifolds, L different physical spaces where the animal can be. So we have an extension of physical Euclidean random matrix to something which was not considered by physicists before, which is a multi-space Euclidean random matrices, where each point, each index I, corresponding to each neuron, can actually be associated to L different positions in L different spaces. So for instance, point I here, the blue point, can have some position in the first space, another position in the second one, another position in the third one, and so on. And for each, and the Cij coefficient of the matrix you will consider is actually the summation over all possible spaces of a function of the distances between the 2 points I and j in the different environments, in the different spaces, which correspond to this definition here. So it's an extension of a standard Euclidean random matrix to a multi-space case, which is quite interesting. So now we cannot consider simple Fourier plane waves anymore because we have a non-coherent superimposition of maps. Yet the spectrum rho of lambda of this random matrix can be actually solved analytically. In fact, what can be found is it's resolvent, the trace of the inverse of Cij minus the mu times the identity matrix. And this can be established with standard random matrix theory. So from that, you can actually go back and to the spectrum. If you want more details, you can look at this paper. And if you have this spectrum, then you can compute the critical capacity when P is large. And our main result is that there is an asymptotic scaling of the capacity, which is a fraction of manifolds that can be stored as you increase the number of points here, anchoring points, which decays as 1 over log P to the D, with some proportionality factor, which depends on the dimension of space and the size of the place split. So what does that mean? It means that, remember that the spatial resolution you have on your manifold is scaling as P to the minus 1 over D. So that means alpha C is decreasing as the absolute value of log epsilon, the spatial resolution, to the minus D. So that means that suppose you have some resolution, epsilon, which is 10 to the minus 3, and you say, oh, 10 to the minus 3 is actually not good enough. I want 10 to the minus 6 compared to the unit width of my space. You move from epsilon to epsilon square, which is a huge increase in terms of accuracy, right? Then what you have to pay is a decrease in terms of capacity. You can store less manifold of higher quality. That makes sense. But the decrease is you decrease only by a fraction. So you see the capacity decrease very slowly with the accuracy, 1 over log epsilon to the D, which is very good news, right? That means recurrent neural networks are actually very good machine for storing very high quality approximation of continuous manifold or many continuous manifold. So I will stop my first lecture here. What I have introduced is a model for a single continuous attractor, which is actually a model which dates back from the 90s. And then I moved to multiple continuous attractors, which are much more complex and interesting problem. I've explained the first learning rule, which is an activity learning rule, which was introduced at the end of the 90s, which gives extensive capacity, but totally uncontrolled quality on the spatial resolution. And then I have explained in details another rule, optimal stability rule, which is related to super vector machine, which actually define quasi-continuous attractors with fully controlled spatial resolution. So we can do much more. You can impose constraints on the sparsity of W. Biologically, it's known that the hippocampus has very sparse connectivity. So what happens if you have a sparse W? Actually, nothing very dramatic happens, except that the capacity is rescaled by the degree of sparsity of a W matrix, as you would expect. You can define more complex geometries, non-homogeneous description of anchoring points, and I want to show this here. This is a case where you have anchoring points which are drawn uniformly in space, except that you have very high density on the diagonal. And you see what is going to happen here in the simulation. You see that the bump of activity is actually very strongly tightened to the diagonal of the space here. So it's a way to control actually the geometry of the attractor. So you can carve in the very high dimensional space some very low dimensional preferred space where the attractor will be located. And perhaps the most interesting question here is the dynamics of learning and the biological plausibility of learning rules. The optimal stability rule is actually quite nice in terms of possibility of doing analytical calculation. But how does it correspond to what is going on in real animals? And I want to end up with the perspective. I'm telling you about a recent experiment, which is absolutely beautiful, which was done by Farouk and Dragol, in newborn animals. So this experiment was published 2 years ago. And what they did is actually, and I'm just summarizing very briefly the experiment, but go to the original paper if you want to have more details. They look at newborn rats, and very briefly, as soon as rats open their eyes, about let's say 13 days after birth, you can see the presence of clay cells. So you can measure the activity of hippocampal cells and see when an animal is the newborn animal is actually running from one side to the other side of the track. Here you see that cells have place fields. So the place fields here were ordered according to the position from left to right of the environment. And of course, they may be not as nice and well-defined as in adult animals. They may be a little bit broader, a little bit further, but essentially they are somewhat localized in space. And so this is what you see when you record the activity of this place cell during the awake period when the animal is actually moving and running from one side to the other side of the animal. But now what is going on when the animal is sleeping? So when the animal is sleeping, you can record the activity of the same cells and decode the virtual trajectory that the animal is actually playing during sleep. How do you do that? Well, you see each cell when it's active corresponds to one position during the awake period. So if you see the same cell acting during the sleep period, you can associate some position here. And you can plot the sequence of position as a function of time as the sequence of sleep activities played in the hippocampus of a newborn animal. And what you see are here as a function of time, you can see here the positions, the position as a function of time for different experiments which were done at, let's say, 15 days after birth, 17 to 18 days, and so on, until to the oldest animal, 23 to 24 days. And you see for very young animals, as soon the place cells exist during the awake period, that when the animal is actually sleeping, the sequence of positions which are played correspond to fixed points. Essentially, there is no change in the position here. And as the animal, you see it's flat over time, it's fixed over time. And as the animal is actually growing older, you see more and more continuous sequences which are played and which for the oldest animal correspond to the whole trajectory corresponding to the whole space. So there is a very interesting question of maturation of attractors, maybe from discrete attractors to fully continuous attractors. And this is fully compatible with the scenario I was mentioning here with the number of anchoring points which is increasing over time. So there is a very interesting question which is open here to be able to describe this maturation line. I stop here for the first lecture, and I'm happy to answer your question now.